let's talk about symmetry. So symmetry is when an object has repeated shapes within it. But in this course, we care about specific types of symmetry that relate to a graph. So symmetry within the graph itself can be helpful, but we particularly care about symmetry that relates to the coordinate plane. So the x-axis, the y-axis, the origin. So symmetry with respect to the x-axis means the graph includes its own reflection over that horizontal x-axis. So you can think of the x-axis as like a water surface that you have whatever the graph is doing above, it's matching that below. So any point above the x-axis, it's going to have its corresponding point below the x-axis that's just going to have the same x value with opposite y values. Symmetry with respect to the y-axis. Now the vertical axis is the kind of mirror. So whatever the graph does on one side, it reflects on the other side. Each point then has its corresponding point on the opposite side of the y-axis. So opposite x values with the same y value. Symmetry with respect to the origin is more of a rotational or a double reflection. So whatever it's doing up here, it's going to do rotated 180 degrees. Or again, you can think of it as it's reflected over the y and then also a second reflection. So not just, it doesn't have the piece reflected over the y, but it gets reflected over the y, then reflected over the x to get down. So we have matching parts that are diagonally opposite, that have opposite x and opposite y. All right, so looking at these types of graphs, you want to identify any types of symmetry they have. So this first one, looking at this, it has matching parts opposite sides of the y-axis. It has that reflection. I could fold it over the y-axis so it would land on top of itself and match up. So it has symmetry with respect to the y-axis. But I'm not going to stop there. I got to check the others too, because as I look at this, it also matches up over the x-axis. I could fold it over the x-axis and it would land on top of itself. So it also has x-axis. And then if I rotate it 180 degrees, right, it's matching up as well. And it turns out if any two of these symmetries are present, they're all three. So you'll never just have two and not the third. You can have all three, or you can have just one of them, or you can have none of them. So this has all three. Looking at the rest of these graphs, we have one other that has all three, this circle. So it has, you know, up and down, side to side. And of course, if you rotate that circle 180 degrees, it stays the same as it started out. All right, looking at this next graph, number 42 here, it doesn't have matching parts reflected over the y-axis. It would have to have those same shapes repeated in the opposite direction. So it doesn't have that. It doesn't have its own reflection over the x-axis. So it doesn't have y, doesn't have x, and it doesn't have its own rotation 180 degrees. Right. So this has none of the types of symmetry that we care about anyway. Number 43 has matching parts on either side of the y-axis, but it doesn't have anything relative to the x-axis. It doesn't have its own reflection there. So this is y-axis only. And looking at the other graphs, 44 also is y-axis only. So that's kind of what those types of graphs look like. You see that reflection matching on either side of the y-axis. 45 is a reflection over the x-axis. So it has its matching parts above and below. That's x-axis symmetry, what those will look like, at least an example of what those will look like, where you have the matching pieces above and below the x-axis. 47 has that rotation 180 degrees. So each piece of the graph, and you kind of see if you have a drawing, a comic, or even a photo of something spinning, a wheel, a fan, you get that sort of S thing happening. So you have this visual of something spinning with its center on the origin. That's the origin type symmetry. It doesn't have x-axis or y-axis because it would need to have those matching parts reflected over either of those axes. So this is origin only, and you get this sort of typically a sort of S shape of some kind. So 48 is also origin. Now, if either of those was shifted, so that center of rotation has to be on the origin. If it's shifted, even if it's that same shape, then we don't care. It wouldn't count. So we only want these symmetries, regardless of what's happening within the graph, the line of reflection or the center of rotation have to be the x-axis or the y-axis or the origin. All right. So some other things we can do this. So if we know the symmetry and we have part of the graph, we can fill it out. You probably did stuff like this even as a kid on a restaurant menu or a, something like that, where you have half the picture and you're supposed to finish the picture. So the first one, we have x-axis symmetry. Then we need to have the matching pieces that are above. We need to match them up below. So I'm going to just go ahead and match the points, and then I can easily connect the dots to draw the lines. The ones that are on the x-axis just don't need to be repeated. They're just still there. So we had 3, 4, then we have 3, -4, 5, 1, we have 5, -1, 7, 3, 7, -3, etc. If it's symmetric with respect to the y-axis, then that point 3, 4, we need to have a -3, 4 to match that. And then the 5, 1 needs a -5, 1. And the 7, 3 needs a -7, 3. And the 8, 0 needs a -8, 0. To get that shape. Pretend my lines are perfectly connecting those dots. Symmetry with respect to the origin. Now each of these pieces needs an opposite x and y. So 3, 4, we're going to have -3, -4. 5, 1, we're going to have -5, -1. And then 7, 3, -7, -3. And 8, 0, -8, -0, which is still just 0. So the only one not changed by any of them, of course, the origin itself is just still the origin. Right, so that's what those would look like. And then, so I already kind of talked about this, the corresponding points. If it's symmetric with respect to the x-axis, then whatever point you have, you're going to have another point with the same x value and opposite y value. Symmetry with respect to the y-axis, we'll have points with the same y value with opposite x values. Every point will have its matching point with that. And for the origin, every point will have a corresponding point with opposite x and opposite y. So we can tell then, without even having the graph, we can look at, if I know the graph has this point and it has this type of symmetry, what other point does it have to have? So symmetry with respect to the x-axis, again, so we're going to have, we have the x-axis, we have those matching points, same x, opposite y. So if there's a 0.32, we got to have 3, -2. -5, 8, then we got to have -5, -8. -4, -2, we got to have then also -4 with +2. Y-axis symmetry, we have points with the same y, opposite x. So if we have the 0.32, we have to have -3, 2 also. -5, 8, then we need to have +5, 8. -4, -2, then we also need +4, -2. And then origin is going to be both opposite. So if we have the 0.32, we also need -3, -2. -5, 8, we got to have +5, -8. And -4, -2, then we also need +4, +2. So that's symmetry.